Let's do one. I think these numbers are probably missing also. Okay, so the thermite reaction, it's a very fun reaction. Powdered aluminum reacts with iron oxide, and it's highly exothermic. Use standard enthalpies of formation to find the heat of reaction for the thermite reaction. So what we want to do here is we've got heats of formation for the products and the opposite of heats of formation for the reactants. Because they're not forming, those are decomposing. So if there are any elements here that are in their standard state, then those are going to end up being 0, so that's kind of nice. So this is going to be the heats of formation of the products, and you have to take into account the coefficients. Because if you have 2 moles of something, it's going to have twice as much energy change. So I've got the heat of formation for aluminum oxide plus the heat of formation, 2 times the heat of formation for iron. So those are my products. Those are the things that are being formed. When something is being decomposed, you change the sign of delta H. So I subtract these guys. So these are the reactants. I have 2 times the heat of formation for aluminum. And I have the heat of formation for Fe2O3. Mm-hmm. Because I made a mistake. It's a very good question. Yeah, I don't know. It's supposed to be an H. Thank you for catching that. Because it says right here, delta H. So then we look these numbers up in tables. Iron, as a solid, is in its standard state. So that's 0. So this one's 0. And aluminum, as a solid, that's the standard state for aluminum. So that one's 0. So we need to look up aluminum oxide and iron 3 oxide. I'm pretty sure those are not going to be in the table, but I'm going to look anyway because I'm an optimistic person. They're not there. Okay. Okay, so I borrowed a student's textbook. This is back in Appendix 2. There are tables of standard thermodynamic quantities for selected substances. And the one we're interested in is delta HF. So I need Al2O3, and it's minus 1675.7. And the one for iron, Fe2O3, is minus 824.2. Yeah, kilojoules per mole. So we're multiplying by the number of moles. How many moles of Fe2O3? 1. So that is, if we're going to keep track of our units, which is never a bad idea, 1 mole times that, the moles cancel out. And how many moles of aluminum oxide? 1. So that's 1 mole. So I end up with 1675.7 kilojoules minus all of this over here, negative 824.2 kilojoules. If you minus a minus, it's adding. So I've got negative 1675 point, I'm missing the pointer. I'm missing the pointer. And I'm going to subtract a negative 824.2. I'm going to get negative 851.5 kilojoules. So the heat of reaction is negative 851.5 kilojoules. Any questions? One more example, and then we're done, I promise. Okay, chemical hand warmers produce heat when they're removed from the airtight plastic wrappers. Here's the reaction. Calculate heat of reaction for this reaction. Calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. Okay, so the heat of reaction for this would be the heat of formation of this Fe2O3 times 2 minus 4 times the heat of formation for iron and 3 times the heat of formation for oxygen. What are the heats of formation for these two guys? 0. There are elements in their standard states, so they're 0. So it's just going to be 2 times the heat of formation for this one, which we just looked up, but I've forgotten already because I don't have room in my head for numbers like that. Minus 824.2. Kilojoules per mole. So that's the heat of formation for Fe2O3. You look it up. And the heat of reaction equals, it's just like final minus initial. It's the products minus the reactants. It's the heat of formation for the Fe2O3 times 2, because there's a coefficient of 2, minus all of the reactants, be 4 times the heat of formation for iron, which is 0, and 3 times the heat of formation for oxygen, which is also 0. So it ends up being 2 times the heat of formation for the Fe2O3.